maybe 2 or 3 exercises on. So first, they say find the direction of the magnetic field acting on the positively charged particle moving in the various situations that are given below. If the direction of the magnetic field force acting on it, it is as indicated. So look at this, they give us the force. So they give us in what direction the thumb is acting, in what direction is the thumb, but they don't give us the field. So we have to apply the second right-hand rule, sorry, the first right-hand rule. Remember that right hand rule 1 says that you have vector velocity and the vector field acting on the same plane. And we have here a particle that is positive, then the force would be perpendicular to that plane. So you are moving, you're curving your fingers from B toward, from the velocity toward the vector intensity of the field, and your thumb would be pointing like this, right? So you have your other 4 fingers here, by your thumb just points in the direction of the force. Remember that this is the right-hand rule, 1. So you say, okay, I would put my 4 fingers here like this. My thumb would be like this, right? So just put your hand in front of the screen of your computer, put the 4 fingers in the direction of the speed, the direction of the velocity. Put your thumb pointing up, curve your fingers. And when you curve your fingers, you see how now the fingers, after being curved, just point toward the screen of the computer. So that means that in this case, the field points toward the screen of the computer. This is the direction of the field. The field points toward the direction, or toward the screen of the computer, enters into the screen of the computer. Now, in the next case, we have now the velocity that is pointing out. So now you must put your 4 fingers just pointing toward you, and the thumb pointing up. Just do that. You know, put your 4 fingers in front of you and your thumb pointing up. So basically, you will see your fingers, your 4 fingers, like 4 little circles like this, and your thumb pointing up. Just do that. And now curve your fingers. When you curve your fingers, you will curve your fingers like this direction. So that means that the direction of the magnetic field in this case needs to be to the right. It needs to be to the right. So initially, you had your 4 fingers pointing toward you, your thumb pointing up. When you curve your fingers, now your fingers are in this direction. So B is in that same direction. Next case, You will put your fingers pointing toward the screen of the computer. Your fingers pointing toward the screen of the computer. You put your thumb pointing to the right. And now, when you put your fingers are going to be pointing downward. So it means that in this case, the vector magnetic field points down. Vector magnetic field points down. So using the right-hand rule, if we know two of the vectors, we can find the third. If we know the direction of two of the vectors, we can find the third vector. Any questions so far? Let's see the next exercise. In the next exercise, they say that a laboratory electromagnet produces a magnetic field of magnitude 1.15 Tesla. A proton moves to this field with a speed of 6 times 10 to the 6 meters per second. So we have a laboratory electromagnet that produces a magnetic field of magnitude 1.15 Teslas. What we know here the intensity of the field. We don't know the direction. It's 1.50 Tesla. They don't mention the direction. Now they say that the proton moves this field with a speed. So we're talking about the scalar, right? So a speed, not the velocity, speed, so no direction. 6.00 times 10 to the 6 meters per second. This is what we know. These are the numbers. So what are the numbers? They say first, find the maximum force. Find the maximum force that could be exerted on the proton. Find the magnitude of the maximum force that could be exerted on this proton. So, what is going on here? If we're talking about the maximum force maximum, we're talking about the maximum force. Force maximum is when velocity and magnetic field are perpendicular. So zeta is equals to 90 degrees and the sine of zeta, sine of 90 degrees is. That is important. Because now to find the maximum force, I know that the formula force equals Q speed magnetic field sine of zeta, as the sine of zeta is 1, because zeta is 90, and the sine of 90 is 1. Now the formula of the force will be reduced to force is equals the charge, the speed, times the intensity of the field. Now, what particle they say is this? They say there is a proton. The charge Q is the charge of a proton. And the charge of a proton is 1.602 times 10 to the negative 19 coulombs. So they didn't explicitly give me the charge of the proton. They didn't give me the charge of the particle, but they say the particle was a proton. Proton have a positive charge, and the positive charge of the proton corresponding magnitude to the charge of one electron, and is 1.602 times 10 to the negative 19 coulombs. Now, once I have that, I can calculate the force without a problem. I say, what is the force? Well, the force on this proton would be the charge, the spin, times the field. So it would be 1.602 times 10 to the power of negative 19 coulombs times the speed, 36.00 times 10 to the 6 meters per second times, now the field, that is 1.50 Tesla. So the force would be, when we calculate this force, 14.42 times 10 to the power of negative 13 newtons, which is approximately 1.44 times 10 to the negative 12 newtons. And here I have the magnitude of the force. Now, second question, they say, what is the acceleration of the proton? The acceleration, I don't know the acceleration now, but I know the force that is acting on this proton, and I know the mass of the proton. The mass of a proton is 1.6726 times 10 to the power of negative 27 kilograms. We know the force calculated is 1.44 times 10 to the negative 12 newtons. So I can calculate the acceleration of this proton dividing the force by the mass of the proton, which is the second Newton's law. When I calculate this acceleration, I get that this is 1.44 times 10 to the negative 12 newtons over 1.6726 times 10 to the negative 27 kilograms. So if you calculate the acceleration now, we get that this acceleration is 0.86 times 10 to the 15 meters per second squared, or in scientific notation, 8.6 times 10 to the 0.6 times 10 to the 14 meters per second squared. And here we have the acceleration, maximum acceleration of the proton. And it's the maximum acceleration because this acceleration was calculated based on the maximum force. This is acceleration calculated with the maximum force would be the maximum acceleration. Now, they ask you two more questions. They say, will the field exert the same magnetic force on an electron moving through the field with the same speed? I would say that a force on the electron that is moving through the field with the same speed, we have the same magnitude. A force, we have the same magnitude, right? because the charge of the electron is the same as the charge of the proton, except the sign. But what is going to change in the case of the magnetic force is the direction. So the direction of the magnetic force of the electron is opposite to the direction of the magnetic field of the proton. Now, later they say, would the electron undergo the same acceleration? Well, now here we have a difference because the acceleration depends on the mass of the particle. And the mass of the electron, the mass of one electron is lower than the mass of a proton. Right? So, if the mass of the electron is lower, when I calculate the acceleration of the electron, which is the force that is the same but in opposite direction, the same in magnitude but opposite direction, divided by the mass of the electron that is lower than the mass of the proton, I will get that the acceleration of the electron is going to be greater than the acceleration of the proton, because the mass of the electron, as I said, is lower than the mass of the proton. Right? So the accelerations are not going to be the same in magnitude. We have not the same magnitude. So the less mass, the lower mass, that the electron have, will make its acceleration higher than the acceleration of the proton. And also in case of the direction, of course, the acceleration of the electron will be in a direction opposite to the direction of the acceleration of the proton, because the electron and the proton are under the action of forces that are acting in opposite directions. Right? So the forces acting on the electron and proton have opposite directions. The forces into the magnetic field have opposite directions, then the accelerations are going to be in the directions of the force. Right? So the acceleration will also have opposite directions. This was a very interesting exercise. This is one of the very interesting exercises. Let me solve at least one more. So we would like to solve one of these where we have a motion following a circular path. Let's see, is this one? Let's see. Yes. In the second, exercise. Let me solve now the exercise number 13. Here's exercise number 13 of your book. And this exercise number 13. Let's keep this others. They say in this exercise, because I want to show you one example where we have a circular path. They say an electron moves in a circular path perpendicular to a magnetic field of magnitude 0.235 Tesla. So there is something important here. So let's read again. An electron moves in a circular path perpendicular to a magnetic field of magnitude 0.235 Tesla. Right? If the kinetic energy of the electron is 3.30 times 10 to the negative 19 joules, find the speed of the electron and the radius of the circular path. Well, we know that we have an electron, so So we can find the mass of the electron in the book, right? They give us here the kinetic energy. They say that the kinetic energy is equal to 3.30 times 10 to the negative 19 joules. If I look for the value of the mass of the electron, I have that the mass of the electron is 9.109 times 10 to the negative 31 kilograms. So with this, I have enough information to find the spin of the electron, because we know that kinetic energy is 1/2 the mass, in this case the mass of the electron, times the square of the spin of this electron. So when you solve for the spin, say 2 times the kinetic energy is equal to the mass of the electron times the square of the spin. So 2 times the kinetic energy divided by the mass is equal to the square of the spin. So this spin would be the square root of 2 times the kinetic energy divided by the mass of the electron. So I can now find the spin. I can say the spin is equal to, substituting 2 times kinetic energy, 3.30 times 10 to the negative 19 joules, divided by the mass of the electron, that is 9.109 times 10 to the negative 31 kilogram. And then when we calculate this spin, we get that this is 0.85 times 10 to the 6, 51, and 10 to the 6 meters per second, which in scientific notation would be 8.51 times 10 to the 5th meters per second. Now, what I know about the speed of the electron, the velocity of the electron, the force, and the power. We know that if I have the electron, we have, depending of course in the direction, depending on the direction of the field. So I'm not representing the field here, but I can represent the field. If I represent the field, if I have, for example, a field pointing over, leaving the plane of the, if I have a field leaving the plane of the screen of the computer, right? So we have a field. They don't give us this direction, right? Just to try to give some context to this problem. So we have a field like this, and the particle is an electron. So remember that the force in the electron is opposite to the force on the proton. So when we apply the right-hand rule, it's opposite. You know that when you have a proton, the direction of the force, right? So if I want to have a force that points toward the center here, or the force if the electron is in this other position, and just be pointing toward the center like this. Okay, I would have to have, okay, I would have to have my velocity pointing to for the top electron here, pointing in this direction, pointing left, like that. Because like that, you put your fingers in the direction of the velocity, you put your fingers now against the field, but remember that it's an electron, and then the force points toward the center. So, if we know this is not netted, right? So they are not really asking about this in the problem. But what I want to show you is that the electron will be following this circular path. The electron will be following this circular path. And this circular path has some radius. So you want to find now what is the radius of that circular path. So we know that in this case, we say, okay, I would make, my magnetic force equal to the centripetal force. So we have done this before. So we say that Q charge of the electron times the speed times the field. We know that the angle is 90 degrees because they say, when it is, in this case, perpendicular, it's moving perpendicular, the path of the motion of the electron is perpendicular to the magnetic field. So all this is equal now to the centripetal force, that is mass of the electron times the square of the speed divided by the radius of the path. We are going to simplify, right, this speed with one of the speed over here, and then we can now solve for the radius. We get that charge of the electron times the field times radius is equal to the mass of the electron times the speed. So the radius will be the mass of the electron times the speed over the charge of the electron times. This is the charge of an electron. Remember that we work with an electron here. So I can now calculate the radius. And I can say that the radius is, say, mass of the electron, 9.109 times 10 to the negative 31 kilogram times the speed of the electron, 8.51 times 10 to the 5th meters per second that we calculated previously, divided by, now we have the charge of the electron that is 1.602 times 10 to the negative 19 coulombs times the intensity of the field, is 0.235 Tesla, 135 Tesla. So you calculate the radius of the path, it will give you approximately 205.91 times 10 to the negative 7 meters, which is scientific notation. Approximately 2.06 times 10 to the negative 5 meters. This is, in this case, the radius of the circular path that this electron. Of course, I want to just clarify again. They didn't give us, any direction for the field. I was just taking one direction for the field, putting the electron there, and showing you, how the force is acting, how the velocity is acting, in order to just like give some context, to this problem, and just to go a little bit beyond of what the problem was about by defining also, the direction that we're going to see for a given direction of the magnetic field. It wasn't really given, but I just picked one direction from the magnetic field, and then I just explained, how to do this part, or the motion.